Hi everyone, and thanks the organizers for this event. I'll present a recent work that I did with Jonathan Ruchman from Bar-Ilan University and my advisor, Professor Ran Sela from Tel Aviv University, which I am the PhD student of Ran Sela. Okay. So let me start with a background. I'm working in the measurement-based quantum computation. It was introduced earlier, but I want to reiterate exactly what is this model. So the idea is that instead of using circuits to do a computation, one can initiate a set of qubits called the input ones, which is the symbol there as qubit number 1, have a dedicated output qubits, which we know in advance in the output, and measuring the qubits one after another after they were initiated in some special states to create a computation from that. So for example, here we have what is called a cluster state, which was also introduced here earlier in lecture number 2. And we have measurements here in the x basis over qubits 1, 2, 3, and 4. And this initiates an identity gates, which basically is doing nothing, like idle gates. So it is some sort of teleportation in the circuit based. The formalisms are equivalent one to another. One can go from one to another there. And the idea here is what here I present one-dimensional computation, but one can extend this to two-dimensional cluster states and so on to have a full universal quantum computation using this formalism. So in one dimension, if we want to do a general rotation, instead of measuring in the x basis, we will measure in some rotated angled basis. And all these angles are in the xy plane. So you either measure in xy or any angle in between to actually create this computation. Now, the results of the measurements do influence the output. So there is a method to correct this via feed-forward Pauli corrections. And let me summarize here. So this is a quantum computation without gates. So there is some entangled states at the start, because if you have a product state, there will be no connection between the input and the output. So you must have some sort of entanglement. The idea of the universality of this model is that you can do any unitary gates applied on the input to get into the output qubits. And the cluster state is what is usually used here as a universal resource. There are many options to choose from. So if you do like simple unitary rotations of the cluster state, then you still can do everything, just measuring some rotated angles and so on. And there are very interesting topological characteristics of this states here. Now, this is very important because all the measurements must be in the xy plane, because if you measure in the z plane in this state, it's sort of doing a cut of your input and output. It's like separating them, and this what actually causes the information to stop. So a z measurement actually kills the information from the input, so you cannot get it into the output. So what actually happens here and how we utilize it, will be the idea of the talk, to use it as a non-unitary gates by measuring in this tilted, which was not actually introduced before our paper. Okay, so the cluster state, just to give you an example in 1D, so yes, there are feed-forward correction, but the cluster state is very simple. It's the eigen ground state of this Hamiltonian in 1D. It may have a periodic boundary condition or open boundary condition, but in all our computation, we usually use open boundary conditions. So just think here that you initiate these states before, and then you measure on this basically to drive the computation after you entangle it with some input state. So this is basically the model. Now, why we would want to use non-unitary gates? So the first reason is that there is a non-equilibrium physics, and they have non-unitary operations in them, like dephasing or relaxation or things that we heard here in this event. And it is important to understand how actually they have phase transition or so on. And if we can study them on a quantum computer, we need some way to implement this non-unitary dynamics in a very precise manner. So this is one reason. The second reason is that many computational methods, for example, if you want to take a matrix and get its eigenvalues or eigenvectors, sometimes this matrix is non-unitary. What usually people do is that they try to encode it in a larger unitary matrix or so on, in a method known as block encoding or so on. So if you have somehow a way to apply a non-unitary matrix, it may be beneficial for that. And of course, there is a very interesting connection between non-unitarity and NP-complete problems. So basically, if you can apply a non-unitary gates on a quantum computer in a 100% certainty, this will introduce a way to solve NP-complete problems such as 3-SAT and so on. So people believe that it is not possible. And I'll show that in our talk we cannot apply them in a deterministic way. So the measurements give you some kind of non-deterministic, non-unitary gates. Okay, so I'll cover the imaginary time evolution protocol to explain an example how we use the non-unitary gates. So first let me show them. I don't want to prove how we got this, but if you measure in this XY plane as I explained, you get unitary gates. So for example, this is a simple rotation. It will take the input in 1 to the output at 3 with some rotation around, I think, this z-axis e to the minus I phi z or something like this. Now, what we try to check, and you can check it with ZX calculus, for example, or you can just try to do the algebra, that if you measure in this rotated angle in the XZ plane, you get a non-unitary action, actually. So in the Z, it is very clear why it happens, but it happens also for tilted angles, which is harder to show, but you can do the algebra and prove. And there is a point of where you apply this if you want to get, some rotation or some another rotation. I don't want to get into the details here what we choose here, but basically any rotation like this, think about this as a imaginary time rotation, e to the minus epsilon z or something like this. So it is doing some kind of event. So what we'll try to do is we try to do imaginary time evolution. So we take a plus state, we try to apply this n epsilon gate, which is e to the minus epsilon z, which is shown here. And the idea is that as we apply them many times, it's like a trotterization of this rotation. We don't need to trotterize it, but here we trotterize it to show because the action is non-deterministic, as we will show later. And you will get at the end the zero state. This is the idea. So as you apply many of the Z, it's like a projection at the end. Okay. So this protocol can be implemented like this. There is a matrix for that. If you measure 0, you will get this. But if you measure 1 in the XY plane that I showed in the previous slide, you will not get this. So there is a post-selection here where you need to post-select on all the measurements in the XZ plane to be 0. So this complicates the protocol, and you need to do a lot of post-selection. So what happens here is that you have a circuit like this for one such non-unitary rotation. And this is the Y rotation, which is rotating you to an XZ measurement angle. And here you need to post-select on 0. This is a part that is because of basis transformation that happens in this e to the minus epsilon z. This whole thing is the e to the minus epsilon z. You need to do some correction. And this is a problem because, as we heard in earlier talks, this is part of a dynamic circuit. So you need to correct according to this measurement. You can do post-selection, but it will be too problematic. If we do like 10 totalization and we need to post-select on 20 qubits, you have a very, very low probability to get all of them 0. So this circuit doesn't work, as I'll show later, but there is a better circuit that if you compactify this part and you move the H somehow in the middle of this control Zs, this is something that you cannot do in the measurement-based quantum computation, but we just optimize the circuit. This do basically the same action, but it saves you a qubit. So now it is more reasonable to do the post-selection on this thing because you basically saved half of the qubits. So as we will show, this is the first circuit, for example, that we run. So you see a lot of post-selection here and feed forward. And what you see is that on IBM quantum computer, IBM Birthband, you get something that seems random at n equals 3 already because of all this feed forward. So I needed to correct all this rotations and so on with this feed forward x. And if you use the actual good circuits that is more compactified, you actually see that the imaginary time evolution do take you to the 0 state as the probability of 0 starts to increase. Of course, it will not be 100% because there are errors on this computer. So we use the compactified version. Now, what we can see here is that if I compare it also to the simulation and noisy simulation of the IBM Birthband, we do get very similar results. So it is not very bad, but as n starts to increase, you do see that it starts to deteriorate. So probably there are some coherent errors in the quantum computer that do not allow it to get there. Yeah, so this is the usual noisy simulator that is available in Qiskit Air, as some of you may use it already. Yeah, maybe I'll comment about the simulator. So here we simulated it. So to simulate it, when you have large circuits, we use the matrix product states. It is very useful to simulate very large circuits of MBQC. So for the people that know, I highly recommend using this and not the usual simulator because you will have a space problem. Your Hilbert space basically grows as the number of qubits, but if you want to simulate like 100 qubits of these measurements, you have a large problem for the exact vector simulation, but if you use MPSs and so on, the entanglement is low enough that you can simulate it effectively. Okay. Okay, how we quantify this non-unitary nature? So the problem, as I said, that you have some kind of non-unitary matrix if you get M0, but you have some another matrix if you get this one measurement. So can we avoid this post-selection? This is the problem. So the answer is probably not. So we didn't achieve this, but we can increase the probability of success. So if I measure 1 instead of 0, I can still correct this wrong measurement by basically trying to correct this action of M1. Think about like applying the inverse of M1 and then try to correct the action with M0. So let me show the idea here. So the idea is that when you have a measurement, you get 0, then you are in the good state that you wanted. But if you got 1, you need to think about another angle of rotation that will give you the correct results. So the idea is that instead of 2 qubits to do the rotation, you have many more qubits, but you have some kind of protocol that allows you to correct the measurements. So if the first one fails, you have the second one to correct it. If both of them fails, you have the third one. At some point, it is not beneficial to use more qubits because, as we can see, So there is some formula for this A's, but as we see, after like 5 attempts, the probability of success kind of plateaus. So you want to use here like 3, 4 attempts. The reason why it plateaus is basically that as you have more and more wrong measurements, the state gets to a very problematic state and so on, so you cannot try to correct it. And there is a relation also for the maximum probability that depends on epsilon. So if you try to totalize with very, very low epsilon, then you can still achieve very, very high probability. And we think about this as the lower epsilon means lower non-unitary nature. So basically you kind of try to move things very slowly. So even if you have some kind of errors in the measurements and so on, you can still correct them because it is a very slow process. But if you try to use very high epsilons, wrong measurements basically kick you to some another completely different things, and it is much irreversible process, let's call it. So we also verified that this protocol is the optimal by a reinforcement machine learning technique. So you can try to give the computer these angles, and the computer tries to guess the angles, and it achieves basically the same formula, which is some sort of exponential number there that grows. So A here is some kind of a function of epsilon. It was introduced before. It's not very important. Think about it as epsilon. And indeed, we achieved the maximum probability according to this technique and also previous papers. Okay, so let me conclude here. So there is a protocol, but we don't know what is the most efficient protocol. So we showed one non-unitary gates, but maybe if you want to implement very complicated non-unitary gates, you may have much better protocols, because one point here that people can ask is why not just use the circuit-based and implement the non-unitary via block encoding and so on. So this gives us the idea what is the resources needed for this non-unitary gate. What happens when the qubits are noisy? Is this protocol robust enough? So, I showed you that you need to be very correct in the measurements and in everything to get the correct state at the end. But if you get noisy readout, for example, or things like that, how this affects the whole thing. And there are questions also about the non-unitary computational power. So basically, what kind of function or things you can do with this non-unitarity if you have some limited resources. This relates to a question that asked before about computational power of topological phases and so on. And thanks you very much for your attention. No, we didn't try to do it for QDITs. I know that there are some universal resource for QDITs. So the spin 1, for example, there are some states. I think it should be more or less similar. We did work with 2 qubits and so on. So we have like non-unitary gates that act on more than 1 qubit. This is a very simple example, but there are some more complicated things. And you can complicate it. So the formalism is very general. The ZX calculus, for qubits, it works very well. I don't know about qubits, so you need to think how you do it.
Maybe can you explain again the motivation for why do you need to do non-unitary gates? I mean, in quantum mechanics, non-unitary is an open system, so for sure you have noise. But maybe computationally you meant something else?
Yes, so for example, think about I want to find all the eigenvectors. So I have a linear algebra problem, Ax equals y. I want to solve it, and A is non-unitary. So usually the algorithms that try to solve these things, they encode it in something like A dagger on the diagonals or something like this. The other diagonal, and then you get a unitary matrix from that. So they try to encode this non-unitarity of the matrix inside a larger unitary matrix. This is also what happens in physics. So basically, all the evolution is basically, if you include everything, should be unitary, but when you look at some subset, it is non-unitary. So maybe it gives you a shortcut to do some calculation. This is something that we try to see, and many people do use the non-unitary gates. So you see many publications that they find shortcuts with non-unitary. For example, this NP-complete problems, which is very interesting. So they show that if you can apply some kind of non-unitary matrix, which is the end matrix, the quantum end or something like this, in very high probability, so I think higher than like, yeah, it should be 1 minus exponential something in the number of qubits, then it is a very, very good, it should allows you to solve actually NP-complete problems. So it is very interesting from that perspective. And actually, even if you have one non-unitary gates, people have proven that you can actually span all the matrices with this. So it's enough to have, like if we have the unitary case, you need like 3 gates or so on, or right. So if you had even one non-unitary, it gives you very powerful, like Clifford plus other gates. It's like the same analog of that.